Here is the problem. We are given three transfer functions. g1 of s equals s plus 2 divided by s times s plus 4. g2 of s equals 1 minus s divided by the product of 0.5 s squared plus 0.5 s plus 1 and s plus 1. g3 of s equals s plus 0.5 divided by s plus 2 times s plus 4. And we are given three plots labeled A, B, and C, each showing the step response of one of these transfer functions. Plot A is a straight line ramping up. The response keeps growing and never settles to a constant. Plot B rises quickly, peaks above its final value, and then decays smoothly back down. A clean overshoot, no dip, no oscillation. Plot C first dips below 0, then climbs and overshoots, and slowly approaches its final value with a small wiggle. Our job: match each transfer function to the right plot and justify every match using only the pole 0 map. No simulation needed. Quick strategy. Three signatures in the S-plane decide the shape of a step response. First, a pole at the origin. A factor of 1 over s in the transfer function is an integrator. The step response of an integrator is a ramp going to infinity, never settling. Second, a zero in the right half plane, sometimes called a non-minimum phase zero. The initial slope of the step response and the final value have opposite signs, so the response must dip below 0 before climbing back up. That dip is undershoot. Third, complex-conjugate poles. If the denominator is a quadratic with negative discriminant, the poles come as a pair sigma plus or minus j omega d, and the step response oscillates around the final value. And one more useful fact. A zero in the left half plane that sits close to the origin, closer than the slowest pole, amplifies the transient and produces overshoot, even when the poles themselves are all real. 4 signatures, 3 plots. Let us read each transfer function. g1 of s equals s plus 2 divided by s times s plus 4. Look at the denominator. It has a factor of s. That is a pole at the origin, an integrator. Whenever an integrator is in the loop, the steady-state value of the step response is infinite. The response cannot settle to a constant, it keeps growing forever. We can compute the steady-state slope using the final value theorem on the derivative. As t goes to infinity, the derivative of the step response, y dot of t, equals the limit as s goes to 0 of s squared times y of s, which equals the limit as s goes to 0 of s times g1 of s. Plug in s times s plus 2 over s times s plus 4, which simplifies to s plus 2 over s plus 4. At s equals 0, this is 2/4 equal to 1/2. So the response asymptotically grows as a ramp with slope 1/2. A straight ramp matches plot A. Answer: g1 corresponds to plot A. g2 of s equals 1 minus s divided by the product of 0.5 s squared plus 0.5 s plus 1 and s plus 1. Two things stand out. First, the numerator is 1 minus s, which is 0 when s equals plus 1. That is a 0 in the right half plane. Right half plane 0 means undershoot. The step response starts moving the wrong way. Second, the quadratic factor in the denominator, 0.5 s squared plus 0.5 s plus 1. Multiply through by 2 to clear the leading coefficient, s squared plus s plus 2. The discriminant is 1 minus 8 equal to -7. Negative discriminant means complex roots, so this factor contributes a pair of complex conjugate poles. Complex poles mean oscillation. Combine these. G2 has both undershoot and oscillation. The step response should first dip below 0, then climb past the final value and oscillate around it before settling. Final value. G2 of 0 equals 1 over 1 times 1 equal to 1. Plot C shows exactly this: a small dip below 0, an overshoot above the final value of 1, and a slow oscillating approach. Answer. G2 corresponds to plot C. G3 of S equals S plus 0.5 divided by S plus 2 times S plus 4. Both poles at -2 and -4 are real and in the left half plane, so no integrator, no undershoot, no oscillation. The response is monotonic. Well, almost. There is one twist. The 0 is at -0.5, which is much closer to the origin than either pole. Slow zeros amplify the transient. To see this, expand the partial fractions of the step response. Y of S equals S plus 0.5 divided by S times S plus 2 times S plus 4, which decomposes into A over S plus B over S plus 2 plus C over S plus 4. Solve. A equals 1/16, B equals 3/8, C equals -7/16. Time domain response. Y of t equals 1/16 plus 3/8 times e to the -2t minus 7/16 times e to the -4t. The initial slope is the derivative at 0, -2 times 3/8 plus 4 times 7/16, which equals +1. So the response shoots up with slope 1, much faster than the final value of 1/16 would suggest. The response overshoots its small final value, then comes back down. Plot B matches: a quick rise, a peak well above the final value, and a smooth monotonic decay back to it. No dip, no oscillation. Answer. G3 corresponds to plot B. Now let us verify the three matches by plotting all three step responses on the same axes, computed from the actual transfer functions. G1, plot A. The response is a straight ramp with slope 1/2, growing without bound. Confirms the integrator. G3, plot B. Sharp rise, peak around 0.14, gradual decay back to the final value of 1/16, around 0.06. No dip, no oscillation. Confirms the slow LHP0, kicking the transient up. G2, plot C. Initial dip below 0, climb past 1, oscillation around the final value of 1, slow settling. Confirms RHP0 plus complex poles. 3 transfer functions, 3 plots, 3 signatures. The S-plane told the whole story before we ever ran a simulation. Summary. The matching is G1 to plot A, G2 to plot C, G3 to plot B. G1. Pole at origin, integrator. Response is a ramp. G2. Right half plane 0 plus complex poles. Response shows undershoot and oscillation. G3. Real poles, no oscillation, but a slow left half plane 0 amplifies the transient and produces a clean overshoot. The big picture. Every step response feature has a fingerprint in the S-plane. A pole at the origin gives a ramp. A right half-plane 0 gives a dip. Complex poles give oscillation. A slow left half-plane 0 gives overshoot. Read those 4 signatures and you can sketch the response of any second or third order system without a simulator.